Tonight, we're going to look at something that sounds simple to ask, but is incredibly hard to answer. Can humans ever reach other galaxies? You've probably seen images of distant galaxies many times before. Scientists talk about them often when they speak about the universe. But here's what most people don't really think about. When you begin to understand how far away these galaxies truly are, when you start to grasp the space between them and us, it changes how you think about travel, time, and human limits. This is not just about fast rockets or future machines. It's about distances so extreme that they push against what our bodies, our tools, and even our ideas can handle. And by the end of this journey, you're going to understand why reaching other galaxies is such a huge challenge, and why space scientists still take this question seriously. Before we go any further, if you enjoy slow, deep explorations like this, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a big difference for this work. Now, let's begin. Space stretches in every direction, far beyond what the eye can see. From Earth, the sky appears dotted with stars, small points of light against a deep black canvas. Each star is a sun, burning with energy far beyond what humans can imagine. Some lie close, others are so distant that the light we see left them thousands or even millions of years ago. Beyond these stars, entire collections of stars, known as galaxies, form islands of matter in the emptiness of space. Each galaxy contains billions of stars, and each star may host planets. Yet, even these galaxies are only a small fraction of the universe. The universe is vast beyond comprehension, stretching far beyond what we can observe, beyond the limits of our instruments, and perhaps beyond the bounds of what humans will ever reach. To grasp the distances between galaxies, scientists use the light year. A light year is the distance that light travels in 1 year. Light moves at 299,792 kilometers per second. In 1 year, it travels nearly 9.5 trillion kilometers. These numbers are so large they are hard to imagine. If one were to travel at the speed of a modern jet, it would take billions of years to cover even a fraction of a single light year. The nearest star system beyond our Sun, Proxima Centauri, is just over 4 light years away. Even at that distance, human-made spacecraft would take tens of thousands of years to arrive. The nearest large galaxy, Andromeda, is more than 2 million light-years away, a distance that defies ordinary human comprehension. These scales place human travel into a context that seems impossible with current technology. Galaxies themselves are not evenly distributed. Some are isolated, floating alone in the darkness, while others gather in clusters containing hundreds or thousands of galaxies bound together by gravity. These clusters are not static. They move, rotate, and interact over millions of years. Gravity shapes their paths, pulling them into formations that stretch across millions of light years. When observing these structures, scientists often use telescopes that can detect not only visible light, but also radio waves, infrared, and X-rays. Each type of observation reveals new detail: the heat of stars forming in dusty clouds, the glow of massive black holes at galactic centers, and the faint outline of galaxies far beyond the reach of ordinary sight. Even within a single galaxy, distances are enormous. The Milky Way, our home galaxy, is about 100,000 light-years across. Traveling from one edge to the other at the speed of light would still take 100,000 years. Within this space, stars, gas clouds, and dust float in a delicate balance shaped by gravity. Spiral arms twist around the center, and clusters of stars drift slowly, pulled by the combined mass of the galaxy. Between galaxies, the void is even greater. Space is not empty, but nearly so. Intergalactic space contains sparse gas and dust, cosmic rays and dark matter, but it is overwhelmingly vast and mostly empty. The emptiness itself becomes a barrier to travel, because even at high speeds, crossing millions of light-years takes immense time and energy. Our observable universe extends about 46 billion light-years in every direction, a region defined by the limits of light reaching Earth since the universe began. Beyond this, the universe may continue indefinitely, perhaps infinitely. Within this vastness, galaxies are carried along by the expansion of space itself. Distant galaxies appear to move away from us, a result of the universe stretching over billions of years. This expansion affects distances in a way that makes intergalactic travel even more challenging. Even if a spacecraft could move at near-light speed, the space between galaxies continues to grow, increasing the journey length over time. To understand these distances in practical terms, consider the fastest human-made objects. Voyager 1, launched in 1977, travels at about 17 kilometers per second. At this speed, reaching Proxima Centauri would take more than 70,000 years. Reaching Andromeda would take tens of millions of times longer. The gap between human experience and cosmic scale is immense. Spacecraft speed, energy requirements, and time all grow as distances increase. Scientists often express these challenges not only in numbers, but also in comparative scales. If the solar system were the size of a city, the nearest stars would be thousands of kilometers away, and the nearest galaxy would lie on a distant continent, unreachable by ordinary means. Within galaxies, distances still test human understanding. Stars appear close in the night sky, but many are separated by light years. The nearest stars are invisible without telescopes, their light too faint to see with the naked eye. In star-forming regions, clouds of gas and dust stretch across tens or hundreds of light years, collapsing under gravity to form new stars. Black holes, remnants of massive stars, occupy regions smaller than a city, yet influence matter across light years. Observing these structures requires instruments that can detect minute changes in light, gravitational effects, or high-energy emissions. These observations reveal the structure and scale of galaxies and the complexity of cosmic systems. Galaxies themselves vary in shape, size, and composition. Spiral galaxies, like the Milky Way, have rotating arms of stars, gas, and dust. Elliptical galaxies are smoother and older, containing fewer young stars. Irregular galaxies have no defined shape and often result from collisions. Each galaxy contains stars of various ages, planets, and interstellar matter. Clusters of galaxies form even larger structures, connected by filaments of dark matter and separated by vast voids. The scale of these structures emphasizes how minuscule human constructs are in comparison. Even light, the fastest entity in the universe, takes millions or billions of years to travel between these cosmic islands. Despite the enormity, humans continue to measure, map, and understand these distances. Advanced telescopes scan the sky in multiple wavelengths, recording millions of galaxies and cataloging their positions, movements, and properties. Observations reveal patterns in galaxy distribution, motion, and interaction. Scientists measure redshift to determine how fast galaxies are receding, calculating their distance from Earth and the universe's rate of expansion. Each measurement adds context, forming a map of the observable universe and providing a framework for understanding how far humans would need to travel to reach other galaxies. Grasping intergalactic distances is not only a matter of numbers, it is a matter of perspective. Traveling to the next galaxy is not like crossing an ocean or even a solar system. It is an endeavor that stretches across millions of years of light travel, across immense emptiness, and against the expansion of the universe itself. Even with theoretical propulsion at near light speed, journeys would last longer than human lifespans by orders of magnitude. Yet, the human drive to understand these distances remains. Mapping the universe, measuring its structure, and calculating the positions of galaxies forms the first step toward imagining what it would take to reach them. In the quiet of space, distances shape everything. The stars and galaxies observed from Earth are markers of both time and distance. Light from distant galaxies tells a story of the past, showing how they appeared millions or billions of years ago. The more distant the galaxy, the further back in time we look. Observing Andromeda only 2.5 million light-years away, we see it as it was millions of years ago. For galaxies billions of light-years distant, we see the universe as it was near its beginning. These measurements reinforce the scale of space, demonstrating the vast gap between human travel capabilities and the distances that separate galaxies. Even the concept of nearby in space carries different meaning. Proxima Centauri is near in cosmic terms, yet the journey would last tens of thousands of years at current speeds. Andromeda, close in relative galactic terms, is 2 million light-years away. The Virgo cluster, containing thousands of galaxies, is over 50 million light-years distant. Mapping these distances highlights the extreme challenges posed by intergalactic travel. The universe is vast, structured in complex layers and full of motion, yet for all its immensity it remains measurable and understandable through science. Understanding distances sets the stage for every consideration of travel beyond Earth. It defines the limits of human ambition, the scale of energy required, and the timeframes involved. The first segment of this story frames the immense challenge. Humans are small, fragile, and slow compared to the scale of the universe. Stars and galaxies are not points to cross quickly. They are faraway islands in a sea of darkness, separated by distances that stretch the imagination. Science provides the tools to measure, comprehend, and visualize these distances, laying the foundation for understanding whether humans could ever hope to reach other galaxies. In this understanding, the true enormity of the cosmos becomes clear, a vast and intricate stage on which all of human exploration is just beginning. The universe is vast, but the laws of physics create boundaries that cannot be crossed. Among these, the speed of light stands as the ultimate limit. Nothing with mass can reach or exceed this speed. Light travels at almost 300,000 kilometers every second, fast enough to circle Earth more than 7 times in a single second. Even this immense velocity, however, is only a beginning when considering the distances between galaxies. The nearest galaxy beyond the Milky Way, Andromeda, lies over 2 million light-years away, traveling at light speed. The journey would still take more than 2 million years. This reality defines the first barrier to intergalactic travel. No matter how advanced human technology becomes, The speed of light sets a boundary that cannot be broken. Albert Einstein's theory of relativity explains why this limit exists. As an object moves faster, its mass effectively increases, demanding more and more energy to accelerate further. Approaching the speed of light requires energy beyond what any known source could provide. Spacecraft cannot simply keep adding fuel to reach faster speeds. Energy grows not linearly, but exponentially, becoming infinite at the speed of light. This principle is not a suggestion or guideline. It is a fundamental feature of how the universe operates. Every particle, every spacecraft, every human body is subject to this law. Time behaves differently at extreme speeds. As an object moves faster, time for it slows relative to those left behind. Astronauts traveling near light speed would experience days while years pass on Earth. This effect, known as time dilation, is real and measurable. It has been observed in particles moving close to light speed in laboratories and in satellites orbiting Earth, whose clocks run slightly faster than clocks on the planet. Time dilation offers a strange advantage. Travelers could, in theory, cross long distances and age less than those who remain stationary. But it also complicates travel because the energy needed to approach such speeds is far beyond current capabilities. Human-made spacecraft move at tiny fractions of light speed. Voyager 1, the fastest probe relative to the Sun, travels at about 17 kilometers per second. At this speed, it has taken decades to reach the edge of the solar system and would require tens of thousands of years to reach the nearest star. The Parker Solar Probe, the fastest object ever launched, reaches speeds of nearly 200 kilometers per second at closest approach to the Sun. Even this speed is less than 1,000th of the speed of light. Comparing these numbers highlights the vast gulf between human engineering and the requirements of interstellar or intergalactic travel. Acceleration presents additional limits. Human bodies can endure only limited forces without harm. Sustained high acceleration could crush organs or make movement impossible. Engineers must design propulsion that balances thrust, efficiency, and human safety. Even unmanned probes face limits. Accelerating too quickly consumes enormous energy, and deceleration at the journey's end requires equal effort. Spacecraft moving for decades or centuries face constant decisions about fuel, propulsion, and trajectory. Each choice is constrained by physical laws that cannot be bypassed. The energy requirements to approach light speed are staggering. For every increase in velocity near the speed of light, energy must increase dramatically. Rockets using chemical fuel cannot provide enough energy to reach even a small fraction of light speed. Advanced concepts such as nuclear propulsion, antimatter engines, or fusion drives have been proposed, but they remain experimental. Antimatter, for example, offers the highest energy density known, but producing and storing sufficient quantities safely is far beyond current technology. Even if these systems were perfected, accelerating a large spacecraft to a meaningful fraction of light speed would take decades of constant energy input. Relativity also changes the way distance is perceived at high speeds. As velocity increases, the distance in the direction of travel contracts from the traveler's perspective. A journey that appears to take millions of years from Earth might seem shorter to those aboard a near-light-speed ship. This contraction does not reduce the absolute distance, nor does it circumvent the energy barrier. It is a curious feature of space-time, confirming that speed, distance, and time are deeply connected. Any planning for intergalactic travel must account for these effects, both in terms of physical engineering and mission timelines. Even if humans built a spacecraft that could approach these velocities, the risk of collision with even microscopic particles becomes critical. Space is not completely empty. Tiny dust grains traveling at relativistic speeds can cause catastrophic damage to any object. At 1% of light speed, a collision with a particle could release energy comparable to a small explosive. Shielding for such conditions must be robust, adding more mass and therefore requiring more energy to accelerate. This feedback loop of mass, energy, and velocity illustrates how speed limits constrain every aspect of design for interstellar and intergalactic missions. The difference between the fastest human-made objects and the requirements for intergalactic travel is staggering. Reaching a galaxy millions of light-years away would require speeds that are a significant fraction of light speed. Even reaching 10% of light speed would take enormous advances in energy storage, propulsion, and materials science. Every increment in speed increases energy requirements exponentially. At these extremes, time dilation offers little consolation if propulsion and energy limits remain unsolved. The physical laws of the universe remain absolute, imposing boundaries that cannot be ignored. Understanding these limits frames the next steps in contemplating travel between galaxies. The speed of light is not just a number. It defines the structure of space, the rhythm of time, and the challenges of exploration. Human ambition to cross galaxies is constrained by these unyielding laws, yet knowledge of them also provides a clear map of what must be overcome. Physics does not prohibit dreaming, but it shapes the conditions, setting strict requirements on energy, acceleration, and travel time. Any realistic plan must confront these realities directly. As scientists calculate potential missions, they use relativistic equations to model energy needs and travel times. These calculations reveal that conventional propulsion is insufficient. Approaching even 1/10 of light speed requires energy and fuel far beyond current technology. Hypothetical designs, such as light sails propelled by powerful lasers, suggest alternative approaches, but each must contend with mass, acceleration, and energy constraints. Speed is the core barrier, because no known technology can circumvent the physical limits set by light. Even the concept of distance itself changes at relativistic speeds. From the traveler's frame, distances shrink, but this does not reduce the energy needed to move mass at near-light speeds. Every particle, every structure, must endure the combined effects of acceleration and collisions with interstellar matter. These challenges exist even before considering the length of the journey. To reach another galaxy, spacecraft must survive decades, centuries, or longer in motion while maintaining structural integrity, power, and communication. Relativity imposes a framework that defines what is possible and what is currently beyond reach. The slow movement of human probes emphasizes the vastness of cosmic distances. Voyager 1, after more than 40 years of travel, has only reached the edge of our solar system. At current speeds, it would take over 70,000 years to reach the nearest star, and millions of times longer to reach Andromeda. Parker Solar Probe, though faster, travels only a tiny fraction of the necessary speed for intergalactic travel. These comparisons show that achieving meaningful velocities relative to cosmic scales is a challenge of unprecedented magnitude. Relativity also provides insight into planning for future missions. Time dilation, length contraction, and energy requirements all interact. The faster a spacecraft travels, the more relativistic effects dominate calculations. Engineers must anticipate how propulsion, energy, shielding, and navigation will operate in this context. Even modest fractions of light speed require new materials, energy sources, and long-term systems management. The speed limit of light is absolute, but understanding its consequences guides scientific planning and exploration. Ultimately, the universe enforces a boundary. Speed, mass, energy, and time are linked in ways that define what can and cannot be done. Light speed is a ceiling, not a guideline. Human-made spacecraft are slow in comparison to cosmic distances. Acceleration is limited by energy and biology, and the relativistic effects of high-speed travel reshape every measure of distance and time. Recognizing these limits is the first step in imagining the possibilities of intergalactic travel. Even in the face of these barriers, science continues to explore alternatives, measure outcomes, and seek practical paths toward understanding how far humanity might eventually reach. Moving through space requires propulsion, the force that pushes a spacecraft forward. On Earth, rockets rely on the reaction of expelling gas. Chemical rockets burn fuel and expel exhaust to generate thrust. This simple principle, known for centuries, powers almost all human spacecraft. From the Saturn V that carried astronauts to the Moon to the rockets launching satellites today, chemical propulsion is reliable and well understood. Yet its power is limited. The amount of energy contained in chemical fuels is small compared to what would be needed to travel even a fraction of light speed. A rocket burning chemical fuel cannot reach nearby stars within human lifetimes. Chemical rockets are effective for leaving planets and maneuvering in space, but they are far from sufficient for interstellar or intergalactic travel. Ion drives offer a different approach. Instead of burning fuel quickly, they expel ions at high speed using electric fields. The thrust is weak, but it can be applied continuously for years. NASA's Deep Space One and Dawn missions used ion propulsion to travel across the solar system efficiently. This technology is far more fuel efficient than chemical rockets, making it suitable for long-duration missions. However, ion drives accelerate slowly. Even operating for decades, they can reach only a tiny fraction of light speed. The trade-off is clear: continuous, efficient thrust versus the enormous speed required to reach other galaxies. Nuclear propulsion introduces the possibility of much higher energy density. Nuclear thermal rockets use nuclear reactions to heat propellant, creating higher exhaust velocity than chemical engines. Nuclear electric propulsion converts nuclear energy into electricity, which then powers ion or plasma drives. These systems could, in theory, achieve much higher speeds than chemical rockets. They would still require massive engineering efforts and careful shielding to protect both equipment and crew from radiation. Safety, materials, and energy management are the primary challenges. Even if perfected, nuclear propulsion would remain orders of magnitude too slow for travel between galaxies within human lifetimes. Scientists have also considered exotic concepts for propulsion. Antimatter engines promise energy density far beyond any other source. When matter and antimatter meet, they annihilate, releasing energy equivalent to the mass of both particles multiplied by the speed of light squared. A small amount of antimatter could provide enormous thrust. Producing antimatter, however, is extremely difficult. Particle accelerators create only tiny amounts at great cost. Storing antimatter safely without it contacting normal matter is another enormous challenge. While antimatter engines are theoretically capable of approaching relativistic speeds, practical use is far from reality. Fusion drives take inspiration from the processes powering stars. Fusion fuses light atoms, such as hydrogen isotopes, into heavier ones, releasing energy. The energy density is high, far exceeding chemical fuel, and could provide continuous thrust. Experimental fusion reactors on Earth are still in early stages, and creating a controlled, sustained reaction in a spacecraft is even more difficult. Fuel must be confined, energy extracted, and radiation shielded. A fusion-driven spacecraft could reach a small fraction of light speed, but decades or centuries of development would be required. The energy is abundant in principle, but technology has yet to catch up. Light sails represent a different principle entirely. Instead of carrying fuel, they rely on pressure from photons, particles of light, to push a spacecraft. Powerful lasers could accelerate a sail continuously over long distances. Theoretically, light sails could reach significant fractions of light speed without massive onboard fuel. Challenges include building ultralight, durable materials, maintaining laser focus over astronomical distances, and navigating space. Even small particles of dust or micrometeoroids could damage a sail traveling at relativistic speeds. While promising, light sails remain experimental and untested at interstellar scales. Each propulsion method has strengths and weaknesses. Chemical rockets provide high thrust for launch, but cannot sustain long acceleration. Ion drives and nuclear engines offer efficiency and longer-term thrust, but cannot reach relativistic speeds. Exotic methods like antimatter and fusion promise enormous energy, but face immense technological barriers. Light sails remove the need for fuel, but rely on precise external energy sources and extreme engineering. The common theme is that energy, mass, and material limitations define what can be achieved. Every system requires trade-offs between thrust, acceleration, efficiency, and safety. Energy storage is another constraint. High-speed travel requires enormous amounts of energy. Carrying fuel increases mass, which in turn increases energy needed to accelerate. This creates a loop of growing mass and energy demand. Spacecraft must balance energy availability, propulsion method, and mission duration. Current technologies allow long missions within the solar system, but sending humans or large probes to other galaxies would demand energy beyond anything produced today. Even future nuclear or fusion systems must overcome limits in power generation, shielding, and reliability. Engineering challenges go beyond energy. Spacecraft structures must endure acceleration, radiation, and collisions with interstellar particles. Even tiny grains of dust striking at high speeds could damage critical systems. Materials must be strong, but light, heat-resistant, and radiation-proof. Propulsion systems must operate continuously for years or decades without failure. Navigation, communication, and life support add complexity. Each new system must work in concert with propulsion, requiring careful design and testing. The larger the spacecraft, the greater the challenge. Practical considerations also shape propulsion. Launching from Earth requires overcoming gravity, which consumes a large fraction of fuel. Efficient propulsion in space must minimize mass while maximizing acceleration. Any long-term mission must provide fuel or energy that can sustain travel over decades, centuries, or longer. The balance of mass, energy, and propulsion defines what is technically possible. Even small advances in engine efficiency can dramatically affect mission feasibility, but no current technology can close the gap to intergalactic speeds. Historical progress in propulsion shows a pattern of gradual improvement. Rockets have evolved from simple chemical engines to ion and nuclear concepts. Efficiency has increased, thrust has improved, and missions have grown more ambitious. Each step demonstrates the value of incremental advances, but also the limits imposed by physics. Reaching other galaxies is not a matter of building bigger rockets alone. It requires new physics or energy sources far beyond what has been demonstrated. Each proposed method highlights both possibilities and limitations. Future propulsion may combine multiple methods. A spacecraft might use chemical rockets to escape planets, nuclear or fusion engines to accelerate in space, and light sails to achieve additional speed over long distances. Hybrid systems could maximize strengths and minimize weaknesses, but integration would be complex. Engineering must solve not only propulsion, but energy management, shielding, structural integrity, and mission logistics. Each factor interacts with the others, forming a network of constraints. Even with perfect propulsion, time and distance remain daunting. Accelerating continuously at 1/10 of light speed would take decades, and slowing down requires equally careful planning. Any attempt to reach another galaxy would require careful attention to energy, materials, and propulsion. The laws of physics, particularly relativity, remain firm boundaries. Propulsion can bring humanity closer to these limits, but cannot overcome them. Understanding the constraints shapes realistic expectations and guides scientific exploration. Exploring propulsion in detail shows the scale of the challenge. Chemical rockets launch humans into space, but cannot carry them between stars. Ion and nuclear drives extend the range and efficiency, but remain slow. Antimatter, fusion, and light sails hold theoretical promise, but face technological barriers that are immense. Energy, mass, and structural challenges interact to define limits. Every method illustrates how far humans have come and how far they still must go to approach intergalactic speeds. In considering propulsion, one also considers the spacecraft itself. Large ships require larger engines, more fuel, and stronger materials. Small probes require precision and efficient energy use. Long-duration missions must maintain propulsion over decades or centuries. Each step demands careful calculation of forces, mass, and energy. Propulsion cannot exist in isolation. It interacts with all aspects of space travel, including navigation, shielding, and life support. The balance of these systems defines feasibility. Ultimately, propulsion sets the boundary between possibility and impossibility. Without sufficient energy and thrust, even the most ambitious designs cannot reach the stars, let alone other galaxies. Every proposed system demonstrates the interplay between physics, engineering, and human ambition. Understanding propulsion helps define what steps are achievable in the near future and what remains a distant goal. The challenge is not simply building faster engines, but integrating energy, materials, and physics into a system capable of surviving the vastness of space. Traveling through space is not only a matter of speed or propulsion. The environment of space itself presents challenges that are extreme, constant, and unyielding. Beyond the protective shield of Earth's atmosphere, cosmic radiation strikes continuously. High-energy particles from the Sun, distant stars, and supernovae can penetrate spacecraft, damaging electronics and threatening human health. On Earth, the magnetic field and thick layers of air provide protection. In space, humans must rely on shielding and distance to reduce exposure. Even small amounts of radiation over long periods can increase the risk of cancer, impair cognitive functions, and damage tissues. Designing spacecraft with sufficient shielding adds mass, which in turn increases the energy required for propulsion. Microgravity, the near weightless condition of space, introduces another set of problems. In low gravity, bones lose density, muscles weaken, and the cardiovascular system adjusts in ways that can cause long-term health issues. Astronauts aboard the International Space Station, living in microgravity for months, experience measurable loss of muscle mass and bone strength. Exercise regimes mitigate some effects, but prolonged exposure beyond the duration of current missions remains largely untested. For interstellar or intergalactic journeys, crews would live in microgravity for years or decades, creating an urgent need to understand and counteract these biological changes. Psychological factors are equally important. Humans evolved to live on Earth, surrounded by familiar landscapes, social interactions, and natural cycles of light and dark. Space travel isolates individuals, sometimes in confined spaces, far from familiar social structures. Studies in analog habitats on Earth, such as Mars simulation stations or Antarctic research bases, show that long-term isolation can lead to stress, depression, and interpersonal conflict. Maintaining morale, mental health, and social cohesion is as critical as providing air or food. Crew members must be selected, trained, and supported to handle monotony, limited social contact, and the pressure of responsibility over extended periods. Life support systems form the backbone of survival in space. Air, water, and food must be supplied, regenerated, and maintained over long durations. On current spacecraft, life support systems recycle water from waste, condense humidity, and scrub carbon dioxide from the air. Oxygen is replenished through chemical processes or stored in tanks. Food supply is carefully planned, often relying on pre-packaged meals. These systems work for months or years, but scaling them for decades-long missions introduces new challenges. Reliability must approach perfection, and redundancy becomes essential to prevent catastrophic failure. Closed ecological systems are a potential solution for longer missions. By creating small contained ecosystems, humans can recycle waste into food, water, and oxygen. Plants provide oxygen through photosynthesis and food through growth, while microorganisms process waste. Experiments like Biosphere 2 in Arizona tested these ideas, revealing both promise and complexity. Maintaining balance in a closed system is difficult, as small imbalances can cascade into larger problems. Temperature, humidity, nutrient cycles, and microbial populations must all be monitored and controlled continuously. Scaling such systems for long-term interstellar travel remains theoretical, though research continues. Current missions provide practical lessons. The International Space Station operates as a testbed for long-duration human presence in space. Astronauts live and work for months, studying health effects, life support reliability, and psychological resilience. The ISS demonstrates the feasibility of extended missions within Earth orbit, but the scale is small compared to the needs of interstellar travel. Resupply missions and real-time communication with Earth are available, advantages that would disappear on a journey lasting decades or centuries. The absence of these support systems magnifies every challenge encountered in space. Experiments in analog habitats on Earth simulate conditions of isolation, confinement, and limited resources. Mars analog stations, underwater labs, and polar bases recreate environments where crews must manage limited supplies, operate continuously, and maintain social cohesion. These studies reveal the importance of redundancy, psychological support, and structured routines. They also highlight how minor failures can escalate into serious problems in remote conditions. Lessons learned on Earth inform potential strategies for long-duration space missions, emphasizing planning, discipline, and resilience as essential tools for survival. Radiation shielding remains a critical engineering challenge. Materials such as polyethylene, water, or specialized plastics can absorb high-energy particles, reducing exposure for crew and sensitive electronics. Hydrogen-rich compounds are particularly effective against cosmic rays. However, shielding adds mass, increasing the energy required for propulsion. Spacecraft designers must balance protection against speed and energy efficiency. Emerging ideas include magnetic or plasma shields that could deflect particles, though these remain largely theoretical and untested on large scales. The interplay between physics, materials, and biology defines the boundaries of survivable space travel. Food production in space must account for storage, nutrition, and growth under unusual conditions. Plants grow differently in microgravity, with root orientation and fluid transport affected by lack of gravity. Hydroponic systems, nutrient-rich water solutions, and controlled lighting can enable growth, but long-term reliability and scale remain experimental. Food diversity is necessary to maintain nutrition and morale. Dehydrated and pre-packaged meals are effective for short missions, but multi-decade journeys require self-sustaining production. Each additional kilogram of food or water adds to propulsion requirements, emphasizing the interconnectedness of life support and spacecraft design. Water recycling is equally crucial. Humans require liters of water each day for drinking, hygiene, and cooking. Closed-loop systems on the ISS recover water from urine, sweat, and humidity, purifying it for reuse. The efficiency of these systems is high, but over decades, even minor inefficiencies could become critical. Scaling these systems for larger crews and longer durations compounds the challenge. Resource management becomes a continuous task, demanding careful monitoring, maintenance, and adaptability in the face of unpredictable problems. Air quality must also be carefully controlled. Carbon dioxide accumulation, trace contaminants, and oxygen depletion are constant concerns. Chemical scrubbers remove carbon dioxide, and oxygen tanks or electrolyzers maintain breathable air. Continuous monitoring is essential. Even small failures in life support systems can quickly become life-threatening. Maintaining air quality over decades or centuries in isolated spacecraft demands reliability, redundancy, and automatic control systems that are far beyond current practice. Human health requires monitoring beyond life support. Bone density, muscle strength, and cardiovascular function must be maintained with daily exercise, supplements, and medical oversight. Radiation exposure must be tracked continuously, with measures to reduce risk during solar flares or cosmic events. Psychological monitoring ensures crews remain functional and cooperative. Long-term medical care becomes a major challenge, as spacecraft cannot carry the full capabilities of Earth's hospitals. Remote diagnostics, automated treatment devices, and preventive medicine must all operate in isolation. Social structure aboard spacecraft is another essential consideration. Crews must work, live, and govern themselves in confined spaces. Conflict resolution, decision-making, and hierarchy affect both safety and morale. Small crews may struggle with limited diversity and social interaction, while larger crews require careful organization to maintain order. Studies in analog habitats show that social cohesion and mutual trust are essential for survival. Planning for interstellar travel must account for both technical and social systems. A failure in either could compromise the entire mission. The combination of biological, environmental, and engineering challenges demonstrates the scale of interstellar travel difficulty. Every factor — radiation, microgravity, life support, food, water, air, social structure — interacts with the others. Engineering must provide safe propulsion, while life systems must sustain humans over decades or centuries. Psychological and social factors cannot be separated from biological or technical considerations. The complexity of maintaining human life outside Earth is enormous, and each element must be addressed simultaneously. Experiments aboard the ISS provide insight, but also illustrate limits. Astronauts return to Earth after months in orbit, allowing recovery and study. No human has yet experienced multi-decade exposure to microgravity or isolation. Analog habitats provide partial simulation, but cannot recreate the full scope of interstellar travel. Radiation levels, propulsion isolation, and lack of resupply make real journeys far more difficult. Each experiment informs planning, but every limitation reinforces the challenges of maintaining human life across vast distances and time. Life support, propulsion, and crew health form an interconnected system. Failure in one area can cascade into others. A malfunctioning oxygen scrubber could compound psychological stress. Inadequate shielding could weaken bones and immune systems. Food shortages or contamination could affect morale and physical performance. Systems must be robust, redundant, and continuously monitored. Long-duration interstellar missions will require innovations in engineering, biology, and human factors. Incremental experience in space informs these developments, but true intergalactic travel remains far beyond current capabilities. The study of interstellar travel challenges also guides research priorities. Understanding radiation effects informs shielding and medical countermeasures. Studying microgravity informs exercise and artificial gravity solutions. Observing social dynamics guides crew selection and support. Each domain contributes to a comprehensive picture of human survival in space. The knowledge gained from the ISS, analog habitats, and experimental life support systems lays the foundation for long-term exploration, even if the distances between galaxies remain unreachable for now. Ultimately, the environment of space defines the scale of the challenge. Even with advanced propulsion, humans must survive in conditions vastly different from Earth. Life support must provide air, water, and food. Radiation must be shielded. Microgravity effects mitigated, and psychological and social factors managed. These challenges form barriers that extend beyond technology alone. They shape every mission, every design, and every calculation, emphasizing that the human body is fragile and dependent on careful engineering when venturing into the void between stars. The idea of traveling to another galaxy raises questions not only about speed or propulsion, but also about time. Even at a fraction of light speed, a journey could take centuries. For humans, this requires thinking about life on scales far beyond a single lifetime. One proposed solution is the concept of a generation ship, a self-contained spacecraft where multiple generations of humans live and die before the destination is reached. The ship becomes a floating city, a small ecosystem in motion, carrying the descendants of the original crew across vast distances. The idea has been explored in scientific literature and thought experiments for decades. It requires combining knowledge of biology, sociology, and engineering into a single, sustainable system. Population dynamics are critical for such ships. The crew cannot be too small, or genetic diversity will be insufficient to prevent disease and inbreeding. It cannot be too large, or resources will be strained beyond capacity. Scientists have estimated that thousands of individuals may be required to maintain a viable gene pool over hundreds of years. Birth rates, mortality rates, and life expectancy must be carefully balanced. Social structures must be designed to maintain cooperation, avoid conflict, and provide education. Knowledge and skills must be passed down from generation to generation, ensuring the ship's systems continue to function over centuries. Sustainability is a central challenge. The ship must provide air, water, and food for hundreds or thousands of people over centuries without resupply. Closed-loop life support systems recycle water and nutrients, while plants produce oxygen and food. Energy must be abundant, reliable, and long-lasting. Propulsion systems must remain functional, or the ship may drift aimlessly through space. Maintenance becomes a lifelong task, with knowledge of engines, power systems, and life support passed down through structured education and training. Redundancy is essential. Every system must have backups in case of failure, and materials must endure over long periods without deterioration. Societal structure on a generation ship must balance governance, labor, and education. Crew members must have roles and responsibilities suited to long-term survival. Children grow up within the closed environment and learn the skills necessary to maintain the ship. Decision-making must be distributed or carefully managed to prevent breakdowns in social order. Psychological support is essential to cope with isolation, monotony, and the knowledge that no one aboard has ever seen Earth or another star up close. Maintaining cultural continuity, motivation, and cooperation over centuries becomes as important as maintaining air and water. Scientific proposals suggest various ship designs. Some envision cylindrical habitats rotating to simulate gravity, using centrifugal force to reduce the effects of microgravity on human physiology. Others imagine modular ships, allowing sections to be sealed off for repairs or emergencies. Each design must address shielding against cosmic radiation, including solar flares and galactic cosmic rays. Dense materials such as water, plastics, or metals may provide protection, while magnetic or plasma shields remain a theoretical option. Shielding adds mass, which increases the energy needed for propulsion, reinforcing the interconnected challenges of design, life support, and energy management. Propulsion for generation ships must provide sustained thrust over long periods. Chemical rockets are insufficient, so proposals often include nuclear or fusion drives, ion engines, or combinations of multiple systems. Even with efficient propulsion, maintaining speed and trajectory over centuries requires careful planning. Systems must operate with minimal intervention, as large-scale repairs may be difficult in space. Redundant systems and automated monitoring become critical. The ship must also carry fuel or energy sources capable of lasting decades or centuries, a challenge that links propulsion directly to sustainability. Food production over centuries relies on closed-loop ecosystems. Hydroponics and aquaponics can supply plants and fish for protein, while recycling organic waste regenerates nutrients. Microbial systems may assist in converting waste into usable resources. Energy-efficient lighting and climate control support plant growth in a confined environment. These systems must be monitored and maintained continuously, with each generation trained to manage the balance between consumption and production. Even minor inefficiencies can compound over decades, threatening survival. Maintaining knowledge is another priority. Technical manuals, databases, and educational programs ensure that skills required to operate the ship are not lost. Crews must be trained in engineering, medicine, agriculture, navigation, and governance. Failures in knowledge transfer could compromise mission success. Education must be adapted to new generations, reinforcing both practical skills and understanding of long-term goals. The culture aboard the ship becomes a tool for survival, shaping behavior and ensuring continuity across centuries. Psychological and social factors remain central. Isolation from Earth and the natural world can erode morale. Communities must develop rituals, education, and entertainment to maintain mental health. Conflict resolution mechanisms prevent disputes from escalating. Social cohesion is as vital as mechanical integrity. Generational planning requires attention to cultural continuity, family structures, and social norms, ensuring that each generation retains the knowledge and values needed to continue the mission. Engineering challenges extend to monitoring and repair of all systems. Sensors, automated maintenance, and backup systems must detect and correct problems before they escalate. Propulsion, energy, life support, and habitat structures must all operate reliably without constant intervention from Earth. Materials must resist degradation, corrosion, and fatigue over centuries. Redundancy, modularity, and repair strategies become central to design. Engineers must anticipate failure modes and ensure that crew members are trained to respond appropriately. Even with meticulous planning, risks remain. Cosmic events such as solar storms or supernovae could expose the ship to high radiation doses. Mechanical failures, human error, or disease outbreaks could threaten survival. Probability calculations guide design, but uncertainty remains. Scientists and engineers must prepare for contingencies, designing systems that are resilient, adaptable, and repairable. Risk management becomes a continuous process, as long-term survival depends on anticipating problems centuries before they occur. The concept of generation ships emphasizes the interplay between technology and human biology. Every system must be designed to sustain life, health, and social cohesion over periods far beyond what humans have experienced. Life support, propulsion, food, water, energy, and social systems must integrate seamlessly. Small inefficiencies or failures can cascade, threatening the entire mission. Maintaining a stable, self-sufficient environment for hundreds or thousands of people over centuries challenges every domain of science and engineering. Comparisons in scientific literature highlight the scale of the challenge. Models suggest that even with thousands of people, advanced life support, and efficient propulsion, intergalactic journeys require careful planning, continuous maintenance, and strict adherence to protocols. Resources must be sufficient to cover unexpected events, and social systems must withstand isolation and monotony. The mission is not only a technological challenge, but a social, biological, and psychological one. Every generation relies on the previous one's preparation, and failure in any area could have long-lasting consequences. Long-term maintenance of propulsion and shielding is critical. Engines must operate reliably for centuries, requiring durable materials and effective monitoring. Radiation shielding must remain intact, and repairs must be possible without external assistance. Fuel or energy systems must last decades, with careful management of reserves and recycling. Every system interacts with the others, forming a network of dependencies where failure in one could impact the entire mission. Engineering. For durability, redundancy, and adaptability is as important as initial design. Population management, healthcare, and education integrate into daily life. Reproduction must be balanced to maintain population size without exceeding resource capacity. Medical care must address injury, illness, and age-related conditions over generations. Education ensures that knowledge and technical skills are preserved. Each generation learns to maintain the ship, care for its inhabitants, and plan for the future. Social and cultural continuity becomes a survival tool, shaping behavior and ensuring the mission's long-term success. In thinking about generation ships, one recognizes the interdependence of all systems. Propulsion cannot be considered separately from life support. Energy management affects both habitat and engines. Food production links to population dynamics and resource use. Social cohesion is intertwined with health and morale. The complexity of managing all these elements over centuries illustrates why intergalactic travel is not simply a matter of building a fast rocket. Survival requires a deep understanding of human biology, sociology, and engineering, integrated into a system that can operate independently for multiple generations. Generation ships also force consideration of mission goals and planning. The destination may not be reached by the original crew. Original crew members may never see the stars they set out to explore. Success depends on creating systems that endure beyond individual lifespans. This requires not only technology, but culture, education, and social design. The ship must be a self-sufficient society, capable of maintaining itself and its trajectory across centuries. Human ambition is measured not only in speed, but in the ability to sustain life over time and distance. Ultimately, generation ships illustrate the magnitude of challenges posed by intergalactic travel. Speed alone is insufficient. Life must be maintained, society organized, and systems preserved over centuries. Propulsion, shielding, energy, food, water, and social structure all interact. Knowledge must be transmitted reliably across generations. Engineering must anticipate decay and repair needs. The interplay of biology, technology, and social dynamics defines the boundary between success and failure. These ships represent both a solution to long-duration travel and a reminder of the vastness of the distances humans seek to cross. While humans face immense challenges traveling between galaxies, robots and artificial intelligence offer a different path. Unmanned probes can survive conditions that would be deadly for humans. They do not need food, water, air, or social structure. They can endure radiation, microgravity, and isolation far better than biological life. For interstellar and intergalactic exploration, unmanned probes present a practical alternative. They may take centuries to reach distant galaxies, but unlike humans, they can operate autonomously over extreme periods if properly designed. The absence of life support and the ability to withstand harsh conditions significantly reduces engineering complexity and energy requirements compared with crewed missions. The fastest spacecraft humans have built provide insight into the possibilities. Voyager 1, launched in 1977, travels at about 17 kilometers per second relative to the Sun. It has now passed the edge of the solar system and continues outward into interstellar space. Parker Solar Probe, designed to study the Sun, reaches nearly 200 kilometers per second at closest approach. New Horizons, which flew past Pluto and continues into the Kuiper Belt, moves at around 16 kilometers per second. These speeds, though impressive, remain tiny fractions of light speed. Reaching even the nearest star would require tens of thousands of years, and other galaxies lie millions of times farther. Yet these examples demonstrate that autonomous objects can travel vast distances without human intervention. Future concepts envision probes that go beyond current technology. Self-replicating probes, sometimes called von Neumann probes, could build copies of themselves using local materials. Each probe could then continue exploring new regions, multiplying the rate of coverage exponentially. Such systems, if feasible, would allow exploration of galaxies over extended periods. They would not require humans to be on board, relying instead on automation, robotics, and advanced AI to adapt to new environments, repair themselves, and make decisions independently. The challenge lies in designing systems that can operate reliably for centuries and respond to unknown conditions without human guidance. Nanotechnology adds another layer of potential. Tiny machines, perhaps only micrometers in size, could be used to explore distant star systems with minimal energy requirements. These nanoprobes could carry sensors to study interstellar gas, dust, magnetic fields, or radiation. Their small mass would allow acceleration with light sails or laser propulsion, potentially reaching higher fractions of light speed than larger objects. Energy requirements for propulsion decrease as mass decreases, making them an attractive option for long-duration exploration. These concepts remain speculative, but research into miniaturization, materials, and AI continues to advance. Autonomy is a critical requirement for robotic exploration. Signals from Earth take years to reach distant stars, making real-time control impossible. Probes must navigate, avoid hazards, collect data, and communicate findings on their own. AI systems must process information, make decisions, and adapt to unexpected events. Fault tolerance is essential. Mechanical failures or software errors could halt a mission permanently. Redundancy, self-repair, and adaptive programming are key design goals for long-term autonomous probes. The interplay between energy, computation, and decision-making defines the boundaries of feasibility. Energy sources determine how long probes can operate. Solar power works well near stars, but diminishes with distance. Radioisotope thermoelectric generators, RTGs, provide steady power for decades, using the decay of radioactive material. Nuclear reactors could supply more energy, but require shielding and add complexity. Future probes might rely on fusion reactors or other advanced energy sources. Energy availability limits propulsion, computation, sensors, and communication. Each system must be optimized for efficiency to allow operation over centuries or millennia without resupply. Communication across interstellar distances introduces additional constraints. Even the nearest stars are light years away, and sending signals back to Earth requires time measured in years. Data transmission must be reliable and efficient, compressing information without losing scientific value. Autonomous decision-making allows probes to prioritize what data to send, minimizing energy use while maximizing the value of observations. Strategies for long-range communication must balance bandwidth, energy, and the limitations imposed by vast distances. Shielding is still important, even for robotic explorers. High-energy particles and cosmic rays can damage electronics. Protective materials, radiation-hardened circuits, and fault-tolerant design help probes survive over long periods. Unlike humans, robots can endure higher radiation levels, but failures remain possible. Redundant systems, error-correcting memory, and self-repair mechanisms increase the likelihood of survival over centuries. Designing such systems requires understanding space environments and material limitations. The scaling of self-replicating or multi-probe systems is another challenge. Each probe must be able to identify suitable resources, extract materials, and construct functional copies. Manufacturing errors could propagate, reducing reliability. Control systems must balance replication, exploration, and communication with Earth or other probes. Energy use must be carefully managed, as every replication consumes resources and time. Even with advanced AI, long-term reliability across multiple generations of probes remains a significant engineering problem. Long-duration operation also depends on simplicity. Fewer moving parts, simpler designs, and robust systems reduce the risk of catastrophic failure. Sensors, computers, and propulsion must survive decades without maintenance. Energy-efficient operation reduces the need for large power reserves, making travel at higher speeds more feasible. Engineering for simplicity and durability often outweighs the desire for advanced capabilities when considering intergalactic missions. Robotic explorers can also serve as scouts for future human travel. Probes could map interstellar space, identify hazards, and gather resources ahead of a potential crewed mission. They could test propulsion systems, energy storage, and autonomous operations over long durations. This approach reduces risk for human crews by providing detailed information about conditions en route and at the destination. Robotic missions may be the first step toward eventual human presence beyond the Milky Way, creating knowledge and infrastructure over centuries. The interplay of propulsion, energy, and autonomy defines feasibility. Light sails or laser propulsion could accelerate small probes to significant fractions of light speed, but energy sources must sustain operations for decades or centuries. Nuclear or RTG systems provide steady energy but add mass. AI must process data, make decisions, and adapt without guidance. Long-term reliability requires redundancy, shielding, and self-repair. Each factor influences the others, forming a complex system where success depends on the balance of multiple constraints. Current experiments inform design for autonomous probes. Deep space missions such as Voyager, New Horizons, and Parker Solar Probe provide lessons in long-duration operation, autonomous navigation, and energy management. These spacecraft have operated reliably for decades with minimal intervention. They demonstrate that long-duration robotic exploration is feasible, though the scale and energy requirements for intergalactic missions remain vastly greater. Future designs must expand these principles while addressing challenges of autonomy, energy, and survival over centuries. The possibility of swarms of nanoprobes or self-replicating probes illustrates exponential reach. One probe could create many others, increasing the rate of exploration dramatically. Each unit could perform reconnaissance, analyze matter, or relay data. In principle, this approach could allow exploration of entire galaxies without human presence. The engineering, programming, and energy challenges are significant, but the concept demonstrates how unmanned missions can overcome limits that make human travel nearly impossible. Even without full replication, robotic probes provide a practical path to intergalactic observation. They can endure conditions beyond human tolerance, operate autonomously, and gather data over centuries. Sensors, cameras, and scientific instruments allow detailed study of space environments, magnetic fields, radiation, and distant galaxies. Probes can act as both observers and data collectors, returning information long before humans could hope to arrive. They offer a realistic way to expand knowledge across cosmic distances. Robotic exploration is not without limitations. Longevity requires extraordinary reliability. Self-repair, fault-tolerant software, and energy management must all function without human intervention. Communication delays make guidance from Earth impossible over light years. Redundancy, autonomous decision-making, and careful energy allocation are essential. Probes must survive radiation, dust, micrometeoroids, and mechanical wear. Every design choice balances functionality, mass, energy, and durability, emphasizing the challenges of sustained operation across interstellar and intergalactic distances. Ultimately, robotic and AI-driven probes represent the most feasible approach to exploring galaxies beyond the Milky Way. They bypass biological limitations, survive extreme conditions, and require no life support. Advances in AI, miniaturization, propulsion, and energy management make it conceivable to send probes across cosmic distances. While human travel remains centuries or millennia away, unmanned explorers could gather knowledge, map intergalactic space, and lay the groundwork for eventual human exploration. They embody both practicality and ambition, combining engineering, computing, and scientific curiosity in a form capable of traversing the vast emptiness between galaxies. Traveling between galaxies is not only a matter of speed or life. Support. The journey itself is filled with hazards. Interstellar space is far from empty. Cosmic rays, high-energy particles traveling near the speed of light, bombard any object moving through the galaxy. These particles can damage electronics, degrade materials, and pose lethal threats to biological tissue. For humans, shielding against cosmic rays is essential, but even robust barriers add mass, increasing energy requirements for propulsion. For robots, radiation hardening and redundant systems provide some protection, but prolonged exposure still risks system failures. Over millions of years, even minor damage can accumulate, affecting reliability and mission success. Interstellar dust and micrometeoroids create additional risks. Tiny particles, often no larger than grains of sand, move at high velocities. At relativistic speeds, collisions with even these small particles release enormous energy. A spacecraft striking such debris could suffer catastrophic damage. Solutions include Whipple shields, layers of material designed to absorb and disperse impact energy, and electromagnetic or plasma shields that could deflect charged particles. Predicting collisions over vast distances is difficult, as the distribution of dust and debris varies across the interstellar medium. Navigation systems must account for this uncertainty, balancing speed with protective measures. Temperature extremes and vacuum conditions also affect long-duration travel. Spacecraft in interstellar space experience near absolute zero, while sunlight near stars can heat surfaces to hundreds of degrees Celsius. Materials must endure these extremes without becoming brittle, losing strength, or warping. Thermal control systems regulate internal temperatures, but long-term operation across variable environments adds complexity. Failures in thermal regulation can damage electronics, degrade propulsion systems, and threaten life support on crewed missions. Materials science plays a critical role in maintaining integrity over millennia-long journeys. Navigation across intergalactic distances presents profound challenges. The nearest galaxies lie millions of light-years away. Even traveling near light speed, journeys would take millions of years. Accurate course plotting requires precise understanding of galactic motion, local gravitational fields, and the dynamic behavior of stars and galaxies. Small errors in trajectory compound over time, potentially leading to catastrophic deviations. Navigation systems must continuously adjust course using advanced sensors, autonomous calculations, and pre-programmed corrections. A failure in navigation could leave a spacecraft drifting forever, far from its intended target. Mapping interstellar space depends on both observation and computation. Modern astronomy relies on astrometry, the precise measurement of star positions and motions. Telescopes and observatories chart the locations of stars, star clusters, and galaxies, creating three-dimensional maps of the cosmos. Computational models predict the motion of these objects over time, allowing course corrections to account for gravitational influences and cosmic expansion. Advanced algorithms process massive datasets, integrating observations with physics to plot reliable trajectories. Future intergalactic missions will rely heavily on such computational navigation to maintain accuracy over millions of light-years. Historical context shows the evolution of navigation techniques. Early sailors used the sun, moon, and stars to chart courses across oceans, relying on simple instruments and careful observation. Astronomers later refined positional measurements using telescopes, sextants, and star catalogues. Modern space navigation builds on these principles, but scales them to cosmic distances. GPS and deep space tracking enable navigation within the solar system, while long-range astrometry provides guidance for interstellar travel. Each advance illustrates the interplay of observation, mathematics, and technology, creating a framework for future missions beyond our galaxy. Gravitational influences from stars, gas clouds, and dark matter also affect navigation. A spacecraft traveling for millions of years must account for the movement of celestial bodies that could alter its path. Predicting these changes requires accurate models of galactic dynamics. Even slight miscalculations can accumulate, resulting in significant deviations over time. Autonomous systems must monitor position, detect anomalies, and correct trajectories in real time, combining sensors, star catalogues, and onboard computation to ensure mission accuracy. Communication delays reinforce the need for autonomous navigation. Messages from Earth take years to reach nearby stars, and millions of years for galaxies far beyond. Probes cannot rely on guidance from human operators. AI and onboard computers must make decisions independently, interpreting sensor data, adjusting course, and responding to hazards. This autonomy reduces reliance on Earth, but increases the need for fault-tolerant systems. Navigation must function under uncertainty, with built-in capacity to handle unknown events, such as unexpected dust clouds or gravitational perturbations. Cosmic rays and dust pose additional considerations for trajectory. Instruments must remain protected, and sensors must be calibrated to account for interference from high-energy particles. Micrometeoroid impacts can affect instruments' alignment, reducing navigational accuracy. Redundant instruments and calibration protocols ensure that data used for navigation remains reliable over long durations. The integration of shielding, sensing, and computation becomes essential, forming a robust system capable of guiding a spacecraft across vast, sparsely populated regions of space. The interstellar medium itself is not uniform. Gas clouds, magnetic fields, and varying particle densities create subtle variations that influence motion. Over millions of light years, these variations can nudge a spacecraft off course if unaccounted for. Navigation systems must model these conditions and predict their effects. Sensors may measure local particle densities, magnetic fields, or radiation pressure, providing data to update trajectory calculations. Continuous monitoring and adaptive control ensure that long-term travel remains feasible, even in a dynamic and unpredictable environment. Navigation also requires understanding galactic motion. Galaxies move relative to each other due to gravitational interactions and cosmic expansion. Targets will not remain fixed during multi-million-year journeys. Calculating proper motion, predicting future positions, and adjusting course accordingly are essential. Errors in predicting galactic motion could render the entire journey ineffective. Spacecraft must incorporate models of both local and large-scale cosmic dynamics, integrating observations with theoretical physics to maintain accuracy. Course plotting relies on both pre-mission planning and onboard adjustments. Before launch, mission planners calculate optimal trajectories using detailed maps, gravitational models, and propulsion limits. During the journey, onboard systems continuously measure position relative to known stars or quasars, correcting deviations and adjusting speed. This combination of planning and real-time adjustment minimizes risk and maximizes efficiency. Even minor improvements in navigation reduce energy consumption and increase the likelihood of reaching distant targets successfully. Redundancy in navigation systems ensures survival over long periods. Multiple sensors, backup computers, and alternative algorithms prevent single points of failure from compromising the mission. Calibration routines and fault detection allow the spacecraft to adapt to damage or degradation over time. This robustness is particularly important when journeys span millions of years and when repair or intervention from Earth is impossible. The design philosophy emphasizes resilience and adaptability as much as precision and speed. Advanced computational methods support navigation in intergalactic travel. Simulations model star motion, gravitational effects, cosmic expansion, and interstellar medium properties. Machine learning algorithms can adapt to unexpected conditions, predicting potential hazards, and proposing optimal course adjustments. By combining long-term modeling with real-time data, spacecraft can maintain accuracy even as conditions change. These methods allow autonomous systems to plan centuries or millennia in advance, integrating uncertainty into calculations and maintaining a path toward distant galaxies. Historical navigation principles also guide space missions. Concepts such as triangulation, celestial reference points, and coordinate systems have been scaled up for space. Stars, pulsars, and quasars serve as fixed reference points, similar to lighthouses or landmarks. Observing their positions allows a spacecraft to determine its orientation and location. Combining multiple reference points increases accuracy, compensating for errors caused by local perturbations or sensor limitations. This technique, adapted for intergalactic distances, forms the foundation of autonomous navigation. Finally, navigation integrates with propulsion and hazard avoidance. Course corrections require energy, so efficiency is critical. Avoiding dense regions of dust, radiation hotspots, or micrometeoroid swarms reduces risk but may increase travel distance. Balancing safety, energy consumption, and mission duration requires careful computation. Autonomous systems must weigh trade-offs continuously, adjusting speed, direction, and shielding deployment as needed. The spacecraft's survival depends on this continuous interplay between hazard detection, navigation, and energy management. Intergalactic travel cannot be understood without thinking in terms of time far beyond human experience. Distances between galaxies are so vast that even traveling at nearly the speed of light would take millions of years to reach the nearest neighbor. Time, in this sense, becomes as important as speed or propulsion. The universe itself changes over these immense periods. Galaxies move relative to one another, drawn by gravity or carried by the expansion of space. A star system that seems reachable today may be in a completely different location by the time a spacecraft arrives. Planning must account for motion on cosmic scales, not simply plotting a straight line between points in space. Galaxies are not fixed. The Milky Way, for example, moves at hundreds of kilometers per second relative to nearby galaxies. Andromeda, our nearest large neighbor, is approaching us at roughly 600 kilometers per second. Over millions of years, these motions shift positions by thousands of light years. Intergalactic travel must consider these dynamic coordinates, calculating not where a galaxy is today, but where it will be far into the future. Any spacecraft traveling such distances must integrate precise models of galactic motion, gravitational interactions, and cosmic expansion into its navigation systems. The challenge grows with time, as small uncertainties in motion propagate over millions of years, potentially placing a spacecraft far from its intended destination. The expansion of the universe further complicates matters. Space itself stretches, increasing distances between galaxies over time. Observations of distant galaxies show that light reaching Earth has been stretched or redshifted by this expansion. For a spacecraft traveling across millions of light years, the destination itself moves away, even as the ship approaches. At extreme distances, the rate of expansion can exceed the spacecraft's speed, creating regions of the universe effectively unreachable. Understanding cosmic expansion is therefore essential for assessing what targets are realistically accessible within human-engineered timescales. Redshift is a direct measure of this expansion. As galaxies move away, light stretches to longer wavelengths, shifting from blue to red. The greater the redshift, the faster a galaxy recedes. For intergalactic travel, redshift indicates not only distance, but also relative motion over time. Probes or ships aiming for distant galaxies must account for changing distances and velocities over millions of years. This requires precise knowledge of cosmological parameters, including the Hubble constant and the distribution of matter throughout the universe. Ignoring these factors could result in journeys that never reach their intended target, despite advanced propulsion systems. Cosmic background radiation provides additional context. This faint radiation, a remnant of the universe's formation nearly 14 billion years ago, fills all of space. While it poses little direct threat to spacecraft, it represents the ever-present influence of the universe on any journey. Background radiation sets a baseline environment, influencing temperature, energy measurements, and long-term operation of sensitive instruments. Probes designed for intergalactic travel must monitor this radiation, calibrating sensors and instruments to account for subtle variations across space. It is a constant reminder of the universe's age and the scale at which travel must be planned. Timescales also highlight the contrast between human lifespans and galactic evolution. Humans live for decades, perhaps a century. A single human lifetime is insignificant compared with the millions of years required to traverse intergalactic distances. Even multi-generational spacecraft, planned over centuries, represent only a tiny fraction of cosmic time. Stars form, age, and die over millions or billions of years. Entire galaxies evolve, collide, and merge while a spacecraft is in transit. Understanding these scales is essential to frame the limits of human ambition. Missions that span millions of years require systems, designs, and goals that transcend the perspective of individual lifetimes. The motion of galaxies is influenced not only by mutual gravity, but also by dark matter. Invisible yet massive, dark matter shapes the structure of galactic clusters, altering paths and velocities over cosmic time. Predicting trajectories for intergalactic travel must consider the distribution of dark matter as it affects gravitational fields throughout space. Even small deviations can compound over millions of years, changing the relative position of a target galaxy. Autonomous navigation systems must incorporate models of both visible and invisible mass to remain accurate over long durations. Stars themselves move within galaxies, adding complexity. Each star has its own orbit around the galactic center, and these orbits are influenced by nearby stars, gas clouds, and gravitational perturbations. A destination star system is therefore dynamic, changing position relative to the galaxy and intergalactic space. Trajectories calculated for multi-million-year journeys must integrate these motions to ensure the spacecraft arrives in a region of interest. Knowledge of stellar dynamics, galactic rotation curves, and local gravitational fields becomes as critical as propulsion design or life support systems. Expansion of space also affects communication. Signals sent between galaxies travel at the speed of light, but if the universe is expanding, the effective distance increases during transmission. A message sent today may take millions of years to arrive at a destination that is itself moving. This delay emphasizes the need for autonomous systems, capable of operation without real-time guidance. Probes must make decisions independently, navigate hazards, and adapt to changes in the local environment without relying on Earth-based instructions. Even the concept of time itself is influenced by relativity. For spacecraft traveling at significant fractions of light speed, time aboard the ship slows relative to observers on Earth. This time dilation means that while millions of years may pass for distant galaxies, only decades or centuries might pass for those on board. Understanding the interplay between velocity, time, and distance is essential for planning intergalactic missions. Propulsion, life support, and mission duration are all linked through these relativistic effects. Calculations must integrate physics and cosmology to ensure that timelines remain realistic. Cosmic scales also reveal the impermanence of structures in the universe. Star formation, supernovae, and galactic collisions continuously reshape the cosmos. Regions that appear empty today may contain newly formed stars or dense clouds millions of years in the future. Spacecraft must navigate not only distance, but changing density, gravitational fields, and radiation environments. Predictive models, simulations, and real-time sensors help chart safe paths, but the universe's constant evolution adds uncertainty. Each journey spans eras of cosmic history, placing human-made systems within processes far older than humanity itself. Perspective on time emphasizes humility in planning. Even the most advanced spacecraft designs face durations longer than civilizations have existed. Generational ships or self-replicating probes must endure beyond any current human institution. Maintenance, energy management, and social continuity must account for decades, centuries, or millennia. Systems must be robust, redundant, and adaptable to changes in both environment and mission parameters. Every component is tested not only by mechanical limits, but by the inexorable flow of cosmic time. Understanding these timescales also informs target selection. Nearby galaxies, such as Andromeda or the Magellanic Clouds, are technically reachable within millions of years. More distant galaxies recede faster due to cosmic expansion, potentially moving beyond reach. Selecting feasible destinations requires modeling motion, velocity, and expansion together. Realistic planning acknowledges that while some regions of the universe are accessible in principle, others may be forever out of reach, at least with foreseeable technology. Redshift and the universe's expansion also influence observation. Light from distant galaxies is stretched, providing information about both distance and velocity. Spacecraft relying on visual or spectroscopic navigation must account for these shifts to correctly interpret signals and positions. Instrument calibration, sensor programming, and data processing must adapt to the changes imposed by cosmic time and expansion. Knowledge of cosmology becomes integral to operational planning, as well as to the scientific goals of the mission. Ultimately, framing intergalactic travel in cosmic timescales highlights the limits of human experience. Lifespans are short, civilizations are brief, and individual missions represent a tiny moment in a universe that evolves over billions of years. Designing systems for millions of years' journeys forces consideration of endurance, sustainability, and adaptability on a scale far beyond everyday life. Galaxies, stars, and cosmic structures move, shift, and change while humans plan and operate missions. This perspective emphasizes both the enormity of distances and the patience required to contemplate intergalactic exploration. As humans look further into the cosmos, ideas emerge that challenge conventional understanding of space and motion. Beyond conventional propulsion, theoretical physics suggests possibilities that, in principle, could allow travel across vast distances in ways that seem impossible today. Wormholes, for example, are solutions to Einstein's equations that describe tunnels, connecting distant regions of space-time. If such structures exist, they could allow instantaneous travel between points that are otherwise millions of light-years apart. Wormholes remain hypothetical, but the mathematics suggests that space itself can be curved in ways that create shortcuts. Scientists explore their properties, stability, and the energy required to keep them open. Another concept arises from the idea of a warp drive. In this model, a spacecraft does not move through space in the usual sense, but instead causes space itself to contract in front of it and expand behind it. This would allow the craft to reach effective speeds faster than light, relative to distant observers, without violating the local speed of light. The most studied version, the Alcubierre drive, involves a bubble of space-time carrying the spacecraft. The physics is grounded in general relativity, but the energy requirements are immense. Early calculations suggested that the mass energy needed could be equivalent to that of a planet or more. Later refinements reduce this requirement, but it remains far beyond current technological capability. Theoretical physics provides guidance, but also imposes limits. While mathematics allows wormholes or warp bubbles, practical implementation faces immense challenges. Exotic matter or material with negative energy density may be required to stabilize wormholes or generate a warp bubble. Such matter has not been observed in usable quantities. Even if it could be produced, the energies involved are extreme. These models demonstrate that the laws of physics permit possibilities beyond current engineering, but turning equations into machines remains speculative. Comparing these theoretical models with known physical laws highlights constraints. Special relativity limits how fast conventional objects can move through space. Even the fastest spacecraft cannot approach the speed of light without enormous energy. General relativity allows space itself to curve, producing effects like wormholes or warp drives. But these require conditions and materials beyond practical reach. The interplay between theory and experiment illustrates the gap between imagination and reality. While physics sets boundaries, it also inspires novel approaches that may one day become feasible. Energy requirements dominate any discussion of these concepts. A warp bubble or stable wormhole demands densities and pressures orders of magnitude greater than anything humans can currently generate. For example, moving a ship of modest mass through a warp bubble might require negative energy equivalent to the mass of Jupiter or more. Supplying, controlling, and shaping such energy is inconceivable with present technology. Even if small-scale experiments could demonstrate effects, scaling them to macroscopic travel remains a formidable barrier. Time and space behave differently in these theoretical constructs. In a wormhole, a traveler could move between distant points almost instantly relative to an outside observer. In a warp bubble, the spacecraft's local time may pass normally, while distant points are crossed rapidly. This contrasts sharply with traditional relativistic travel, where approaching light speed causes time dilation. These models allow for scenarios where intergalactic distances could be traversed without waiting millions of years, but they remain speculative. Understanding the relationship between energy, space curvature, and stability is essential before any practical applications could be considered. Despite the speculative nature, exploring these ideas advances physics. Theoretical work tests the limits of general relativity, quantum field theory, and cosmology. Studies of negative energy, exotic matter, and space-time metrics refine understanding of what is possible within physical law. Even if a warp drive or wormhole never becomes practical, research into these areas deepens knowledge of the universe. It highlights the boundary between known physics and imagination, while remaining rigorously grounded in equations and observations. Practical constraints remain central. Stabilizing a wormhole might require precise control of exotic energy across vast distances. Creating a warp bubble demands uniform contraction and expansion of space, controlled precisely to prevent destructive tidal forces. Any error could collapse the structure, release immense energy, or destroy the spacecraft. Unlike conventional travel, small miscalculations carry catastrophic consequences. Engineering solutions must contend with unknowns, and the absence of empirical data makes planning highly speculative. Scientists also consider partial approaches. Manipulating space-time locally at small scales, for instance, could reduce travel time across smaller distances. Experiments in high-energy physics, gravitational waves, or quantum field effects may eventually reveal methods to shape space-time safely. While these remain far from creating a full warp bubble or wormhole, incremental steps in understanding fundamental physics may open doors previously thought impossible. Every insight helps define what is theoretically achievable and what is purely imaginative. Theoretical exploration also informs realistic space mission planning. Understanding extreme energy requirements, exotic matter needs, and stability limits allows scientists to distinguish between what may eventually be achievable and what is fundamentally constrained by physics. This distinction is critical in prioritizing research, allocating resources, and setting expectations for future intergalactic endeavors. It emphasizes the difference between dreaming of instant travel and designing missions grounded in attainable technology. Even within the realm of speculation, scientists must remain consistent with known physics. Any proposed method of faster-than-light or shortcut travel cannot violate causality, create contradictions in relativity, or disregard energy conservation. These principles shape every theoretical proposal. Wormholes and warp drives are constrained by the requirement that mathematics, physics, and cosmic observations remain coherent. Models that break these constraints are considered invalid, even if imaginative. The rigor of physics ensures that speculation does not become fantasy. Long-term feasibility is limited not only by energy, but also by materials and control systems. A ship traveling through a warp bubble must withstand tidal forces, radiation, and quantum fluctuations. Control mechanisms must operate with precision unimaginable with current technology. Material science, energy storage, and computational power all intersect in these theoretical frameworks. Each element must perform flawlessly over durations far longer than any human experience. The gap between theoretical possibility and practical implementation remains enormous, yet the models provide direction for research. Ethical and philosophical questions arise even in theoretical planning. If travel could occur near instantaneously through a wormhole, considerations of causality, communication, and interaction with distant civilizations emerge. The physics may allow movement, but consequences must be anticipated. The universe's structure and dynamics impose boundaries on what travel can achieve without unforeseen effects. Scientific exploration of these boundaries provides insight not only into motion, but into the limits of knowledge itself. Ultimately, these ideas frame human ambition against cosmic reality. Wormholes, warp drives, and space-time manipulation offer glimpses of what could be possible if energy, materials, and control could meet theoretical requirements. For now, they remain conceptual, instructive, and physically grounded rather than immediately achievable. They show that while intergalactic travel is far beyond our current reach, physics does not categorically forbid it. Theoretical research bridges imagination and understanding, helping define the frontier between what is known and what might someday be within reach. Exploring these concepts also encourages innovation in related areas. Energy storage, propulsion, materials science, and AI all benefit from studying the requirements of extreme theoretical models. Even partial progress in one area may enable other advancements in long-duration space travel. By considering the limits imposed by fundamental physics, scientists and engineers gain insight into what incremental steps can realistically move humanity closer to intergalactic exploration. Physics-grounded speculation remains a tool for expanding horizons. By imagining conditions that stretch the limits of current knowledge, researchers test the boundaries of general relativity, quantum mechanics, and cosmology. Wormholes and warp drives function as thought experiments as much as practical proposals. They provide a framework for understanding space-time, energy, and motion in extreme contexts. These frameworks refine theoretical understanding, challenge assumptions, and inspire future generations of physicists and engineers to explore the cosmos in ways that remain consistent with known laws of nature. Looking out into the night sky, humans have long wondered what lies beyond their own galaxy. Stars twinkle like distant lanterns, each a sun in its own system, and each part of a larger cosmic web stretching across unimaginable distances. Contemplating travel to other galaxies forces a perspective shift. The universe is vast, far older than any civilization, and incomprehensibly large compared with human experience. Even the nearest galaxies, visible as faint smudges in telescopes, exist millions of light-years away. Reaching them would require time, energy, and technology far beyond what has been achieved. Yet the very idea stretches human understanding, inspiring questions about possibility, ambition, and the limits of knowledge. Scientific exploration of intergalactic travel combines physics, engineering, and computation. Humanity has learned that speed is limited by fundamental laws. Even at the fastest velocities achieved by our probes, a journey to another galaxy would span millions of years. Time, motion, and distance are intertwined in ways that dwarf human lifetimes. The universe expands, stars move, and galaxies shift relative to one another. Navigation across such vast scales demands knowledge of gravity, radiation, and cosmic dynamics. Every attempt to plan such a journey reveals the vast challenges imposed by the universe itself. Yet, progress is undeniable. Robots and AI have extended human presence beyond the solar system. Voyager, Parker Solar Probe, and New Horizons carry instruments and data into interstellar space, demonstrating that autonomous exploration is possible. Theoretical research into warp drives, wormholes, and other exotic physics highlights pathways, however distant, toward intergalactic travel. While practical implementation may be centuries or millennia away, These studies deepen understanding of energy, materials, and the nature of space-time. They reveal that curiosity, combined with scientific rigor, can push the boundaries of what is conceivable. Challenges remain immense. Biological limitations, propulsion requirements, cosmic hazards, and energy constraints all create formidable barriers. Human travel across galaxies faces issues of life support, radiation, social cohesion, and sustainability. Even multi-generational ships present problems of population management, food production, and system durability over centuries or millennia. Robotic alternatives avoid some of these concerns, yet must still withstand cosmic rays, micrometeoroids, and the relentless passage of time. Every aspect of intergalactic travel underscores the scale of effort needed to bridge the gulf between stars and galaxies. Energy, propulsion, and autonomy form the backbone of exploration. Achieving sufficient velocity for meaningful travel requires advances beyond chemical rockets, ion drives, or nuclear propulsion. Hypothetical methods such as fusion engines, light sails, or space-time manipulation exist in theory, but face enormous energy and materials challenges. Navigation across millions of light-years demands precise mapping, computation, and autonomous adjustment. Even with these tools, cosmic expansion and motion of galaxies mean that destinations shift, requiring continual recalculation. The universe imposes its own timetable, independent of human ambition. Time itself frames the challenge in new ways. Galactic evolution, cosmic expansion, and redshift reveal that the universe is dynamic. A galaxy reachable today may be out of reach in the distant future, or closer in relative terms than expected. Human perception of time is brief compared with the millions or billions of years that define galactic motion. Any plan for intergalactic exploration must integrate this temporal perspective, appreciating that civilizations, lifespans, and even stars are fleeting in cosmic terms. The contrast between human duration and cosmic time underscores both our limitations and our potential to imagine beyond immediate experience. Philosophical reflection arises naturally from these considerations. Even if practical intergalactic travel is currently impossible, the very act of contemplating it expands the mind. It encourages humans to consider their place in a vast universe, to recognize the smallness of individual lifetimes, and to acknowledge the grandeur of cosmic scales. The challenges of distance, energy, and time do not diminish curiosity, they amplify it. In understanding limitations, humans also discover new questions, new methods, and new perspectives on existence itself. The universe becomes not just a destination, but a teacher. Exploration has always shaped humanity. From crossing oceans to walking on the moon, progress occurs incrementally. Robotic probes, space telescopes, and orbital observatories continue that tradition, extending observation and influence. Each mission adds data, refines models, and informs future possibilities. Knowledge itself becomes a kind of travel, bridging space in the mind, if not yet in reality. The act of understanding distant galaxies, of mapping their motions and conditions, is itself an expansion of human presence. We extend our reach through study, computation, and imagination, even when physical arrival remains impossible. Considering intergalactic travel also highlights collaboration. Knowledge builds across generations, institutions, and nations. Physics, engineering, and astronomy converge to tackle problems that no single individual could solve. Sharing data, refining models, and testing propulsion or navigation concepts collectively extend the scope of what humans can achieve. Humanity's ability to dream of intergalactic voyages reflects not only intelligence, but also cooperation, patience, and the capacity to plan across timescales far longer than individual lives. This collective effort demonstrates the unique human combination of curiosity and persistence. The vastness of the universe reminds humans of fragility and resilience. Individual lives are brief, civilizations may rise and fall, yet the curiosity that drives exploration persists. Even if the first intergalactic voyages are unmanned, they represent humanity's desire to reach outward, to observe, and to understand. Knowledge, carried by instruments, AI, and observation, can cross cosmic distances. In this sense, humans leave traces beyond the limits of biology, extending presence through technology and intellect. Exploration thus becomes a form of continuity, linking generations and bridging distances that physical bodies cannot yet traverse. Reflection on cosmic perspective grounds ambition in humility. The universe is immense. Galaxies number in the hundreds of billions, and distances stretch beyond comprehension. Yet humans persist in observing, measuring, and imagining. Intergalactic travel, even if theoretical for now, is a natural extension of curiosity. It challenges the mind to reconcile ambition with reality, possibility with limits, and imagination with physics. Understanding our place among galaxies offers both a sense of smallness and a sense of wonder. It frames human life not as central, but as part of a larger unfolding story of the cosmos. In the end, contemplating intergalactic travel is both scientific and philosophical. It involves propulsion, energy, navigation, hazards, and physics, but it also involves perspective, patience, and reflection. Humans have advanced from wondering about nearby stars to observing entire galaxies, calculating motions, and imagining travel beyond the Milky Way. Every achievement builds knowledge and capability, even if the ultimate journey remains distant. The story of exploration is ongoing, a continuum of effort, thought, and discovery. The cosmos invites observation, understanding, and cautious planning. Whether through robotic probes, AI explorers, or eventual human missions, intergalactic travel embodies the interplay of curiosity and constraint. Challenges are immense, but progress continues step by step. Each advance in propulsion, computation, navigation, or energy management brings humanity closer to engaging with the universe at scales once unimaginable. By embracing both ambition and realism, humans chart a path forward, mindful of the immense distances, energies, and timescales involved. In quiet reflection, the stars remind humans of perspective. Every effort in science, every probe sent, every calculation made, contributes to a larger understanding of the universe. Intergalactic travel may be far in the future, but the desire to reach, understand, and connect with distant galaxies remains present. Humans inhabit a small corner of the cosmos, yet through curiosity, study, and ingenuity, they expand presence into the infinite. Knowledge and imagination become tools to traverse space indirectly, preparing minds and technology for the possibilities that the distant universe may one day offer. We live on a small planet in a vast galaxy, itself part of a universe filled with countless others. The journey to intergalactic travel, whether through imagination, robotic proxies, or future technology, reminds humans of both limitations and potential. Science illuminates challenges, physics sets boundaries, and exploration extends presence. In contemplating the universe, humans find not only questions but purpose, the pursuit of understanding, the desire to reach beyond, and the humility to recognize their place within a cosmos far larger and older than themselves.